Hi everyone. Good evening once again. I hope we're all doing well. Thank you for staying till this time. My name is Ifio, and I would be hosting this call for our September Chilean Lagos technical session. So, next slide. Yeah, before we begin, just like to lay down some ground rules. Like all of us to read it. I'm not going to read everything all at once, but I mean the regular rules that we've been keeping over time. If you learn to be respectful, keep your microphone muted, or your videos, turned off. If you're not the one speaking or you're not the one doing anything, so that we can all hear the main speaker and we can follow through, then let's always put our questions in the chat. We should keep the call to machine learning alone or the scope of the topic, and feel free to ask questions during the Q&A segment. And yeah, let's be respectful to one another. So without like much talk, I'll just be going into this session. So yes, I've done this. Welcome. We're going to the session, then we'll have the Q&A, and then we'll have the announcement and the wrap up. So yes, our session today is on understanding tokenizations in audio and speech language model that will be taken by I don't know how to pronounce the first name. I'm sorry, so I'm going to butcher it. General, I don't know. You know what? I'm just going to say Odun. Yes, sir. Yeah. So a little about you. Odun Ola is a research scientist at Speech, a company building audio and speech tools for creators and businesses, with special focus on African voices. He currently works on the automatic speech recognition team at Speech, a team that recently launched Mansa, an automatic speech recognition model that excels particularly at African named entities. So, yes, let's all welcome Odun to the session. And yeah, on the notes, I really like what they're doing at speech, and that's what prompted me to bring them here for the session. So, over to you, Odun.
Hi everyone. Good afternoon. Good evening. Can you, or if you can hear me, please feel free to drop the message on the chat box. Oh, yes, nice, good. So for the next, let's say 30 to 45 minutes, I'll try to not bore you on this topic. Well, okay, I think I have a slide, so I'll just share my screen also. Um, 1 minute, please. Um, okay, good. Thank you. Can you all see my screen? Is it clear enough? Okay, good, good. So, yeah, as I said, I would try to not bore you as much for the next, let's say, 30 to 45, where I kind of talk about this interesting topic that, so tokenization in general is more or less, I think, is a underrated, it's a very underrated thing in, let's say, NLP in general and in AI in general, because if you think about it, the first layer of input, sorry, I shouldn't. Yeah, so the first layer, so the first input, so whatever you're taking into your language model, whatever your language is being trained on, of course, it's trained on large text, it's trained on our data, it's trained on information, data in general. How would we exactly represent this information to something that computers understand? So if there is a problem in that interface, so there is a communication layer. So if there's a problem in that interface, then of course if the thing you are using to convert your information, your data to what computers understand is faulty, then even though you can have like millions of hours of audio, you can have like thousands of gigabytes worth of tokens or data, your model is just taking nonsense. So people tend to underestimate this part of this area of research, but it's a very, very serious area of research. It's a very, very important area of research. I think young researchers like we should take into account a lot. So yeah, I'm grateful for Ifiona and that team for letting me come up here to talk about this. I'm hoping that yeah, it's something that we would interest us going forward. It's boring research, I trust me, but it's impactful. It's impactful research. So yeah, when we communicate, we use complex systems of words, systems, and sounds. So we as humans are blessed to be able to communicate in multiple ways in general. So we can use our writing, text. That's like the more ubiquitous method. Of course, sorry. Then, of course, we can use our audio, our speech, our voice to convey information. Sorry, I should correct that. That is actually the more ubiquitous method. Can you see my screen? I think someone says, "Oh, okay, good." So I should correct myself. Audio actually is the more ubiquitous method. I'm conversing with you right now with my voice. So I would say text is the second more ubiquitous method of communication, and that's why recently we are seeing people come up with more ways of ingesting, more ways of using audio to train word models that can understand every single thing that we do. Yeah, so we are gradually moving from text only preaching into audio and text. Yeah, so the critical process that we do to convert data into things that computer understand is what we call tokenization. I think I've said that already. So yeah, so language models are they are incredibly powerful. So they can directly interpret raw text or audio. So to unlock their potential, we first construct human language and audio into smaller, manageable chunks, manageable units. So think of it. So we call them tokens in AI. So think of these tokens as fundamental building blocks. So by converting our complex inputs, so by converting these samples of data, be it audio, text, videos. So yeah, you also have some data that can be represented in sort of graphs. So we have things like sequential time series data. So by converting into some sort of token, some sort of representation. So yeah, so models can learn intricate patterns. We enable them to understand and generate or even translate information effectively. So yeah, so think of this as building, like I said, once a model has these building blocks, it can learn how to put them together to understand, generate, or translate. So it's like I am building a sort of translator. So I'm building a sort of human to machine translator, right? Where the human input is be it our voice or audio or text, and then the translated version of it is some representation that language models, neural networks in general can understand. So yeah, that's tokenization in general. It comes in different formats. There are some that are good that are used to do text-based information. So that's why we have things like BP, byte-speed encoding. Where it's an algorithm so that algorithm is basically what it does is that it's kind of splits text into multiple chunks and it assigns a number as each chunk. I'll talk about that in a bit. And then there's audio type tokenization we are doing here. There's of course video. There is all sorts of tokenization. So another interest area of research that is coming up recently is a single tokenizer that can handle all sorts of modalities. So that's something very interesting. Sorry, I tend to talk a little bit fast. So if I sort of drill out, please feel free to put it in the comment. I would do it to come back. Yeah. So um, yeah, so in text, how does notation work in text before we go to audio? So in text, it's pretty intuitive in a way. So I would say intuitive because I would say it's intuitive nowadays because it's basically the de facto way we interact with language models today. If you think about it, ChatGPT is probably what most of us have used in general. So yeah, so that's the way ChatGPT, the way OpenAI tokenizes their text is pretty intuitive in a way. So so most of the time they use algorithm like BPA. But in general, if you look at it from a high perspective, basically what tokenization it takes how it works is that you would split sentences, so samples of data into individual words. You break those words into subwords. For example, like I have a word like I can have a word like in word like let's say some sampling now I can split those that single word into like multiple subwords. So a single token can be sub, another token can be sampled, right? And then in the model's dictionary, quote unquote, we would assign each a number, a numerical value. Let's say 0 is sub, 1 is sample. So and then the length of the number, and then the number of subwords that we can get when we split this text is what we call our dictionary. So I don't know if you guys get what I'm trying to say. So basically, we take every single word and every single sentence, we split each word into subword, and then we assign each word to some sort of lookup table, and that lookup table we call a dictionary. So for each number in the model's vocabulary or dictionary, each number corresponds to each text. So if you want to use the word play, playing, if you want to send the word play or the subword play into the model, would go into our dictionary. That's our tokenizer dictionary. Would look for the number that corresponds to the word play, is that number that was sent into the model. I don't know if you guys, I don't know if you get what I'm trying to say. So if you understand, please put a thumbs up. I think yeah, good, good. So tokenization is so this method of tokenization is not without challenges. So the only segment sentences into subwords that assign them to a model vocabulary can be problematic, especially for languages that differ significantly for English. So when these algorithms were being devised or created, a lot of the focus in the language that people were kind of working with, people were kind of taking into account most was of course English, because English is the most I think it's the most widely spoken language. I may be wrong, but it should be. So a lot of this are going, a lot of this research going technician then in the early stage of in the early stage of this field of research, a lot of it went into English, trying to figure out the best way to split this. But if you think about some special languages like Yoruba, for example, with the diacritics, or some very very niche languages like Amharic, so languages that have a lot of symbols embedded in the textual representation themselves, then this form of organization starts to falter and fail. So in this case, current organization methods can reveal limitations in how language video processes and understand these diverse linguistic structures. So, for example, now if you are familiar with Yorubas, the way Yoruba is written, there's what we call diacritics. So diacritics are sort of like symbols that are assigned at the top of each some letters. I think you have let's say the vowels are R, E, I. I'm not very good at Yoruba, but each so a single letter can have different pronunciations, and then they are differed by that army. So it's called army. That's some symbols that are attached at the top of the letters. So that's an example of a problem. That can be an example of a problem that this kind of organization can face, because this authentication, so it can, so because we have those special symbols in Yoruba, there are some very niche cases where your language will default when it's trying to predict Yoruba based text. Another good example is languages like Hindu or Amharic, where it's fully symbolic in nature. Chinese, for example, this method of tokenization would so it's not exactly suitable for those sorts of languages. If you have time and you have time to like stress test some of these models or some of these niche languages, if you are very fluent in it, you would see some very very funny mishaps happening. And a lot sometimes most times actually, so those mishaps are not as a result of the model being bad. It's a sort of tokenizer not being suitable for those languages. So I don't know if I'm clear enough on that notion. If I'm clear, please. Yeah, good. Okay, so yeah, you can. Yeah, so let's go back into. So this is an example of. I just put this thing to exact to kind of make the whole subword thing a lot more clear. So look at this text, for example. This is how tokenizers work in text. They convert text space. So this is OpenAI GPT-4 tokenizer, right? So this is exactly how OpenAI kind of takes whatever that's as of GPT-4, right? Not GPT new GPT-5. So this is how they take all of your assignment, all of your whatever you put into it. For example, this is how the model sees and represents it. The model inside sees and represents. So you would give it all of this text, and then internally this tokenizer kind of splits into subwords. So you can look if you look at the colors down, you see, so this is how tokenize. So you see that it splits this word into two. So this is one subword, this is another subword. Work in text, and then the full stop now is another subword. And then so they convert text-based characters into subwords, each subword. So you can see that it converts this into subwords, and then so now for each color represents a single token, right? And then each token represents a single number. So we call it token actually. So now the word this might be converted into, let's say it's number zero now, for example. The word is number one, the word how is number two, token number three, something like that. And then so the document splits the sentence, and then for each word it gives it's a number to those words depending on what's the depending on what's the dictionary, and then it's passed into the model, and the model learns to help you cheat your exam or cheat your assignment or something. Sorry about that, but yeah, yeah, let's go on. Okay, good. So now let's go back to audio. Audio is basically what we are here to do. So now let's shift our focus into audio. So challenges of audio is the challenges of tokenization in audio is actually it's much more complex. So audio is a very very special audio and video. So they are a very very special kind of information, a very special kind of data. So they are very high dimension, and they're all called continuous. So yeah, it's a different ball game basically. So audio is much more richer and it's much more complex than text. If you think about it, how would you write audio if you want to write audio? Just think about it. So that might be a very weird question, but just think how would you write audio? How can you represent audio in something that we can see? Just think about it. So audio is a lot more complex than text. So text is a form of discrete type data, discrete type representation. So by discrete, I mean that you can easily kind of see, you can even select certain words and have it represent a particular topic. But audio is a lot more special. So it's hard for us to think about audio in terms of dictionaries or vocabulary or things like that. So it's rich not just in spoken words. So in audio, so in a single audio array or audio sample, we have a lot more information embedded in that representation. You have things like speaker information, you have things like timbre, you have things like amplitude, you have things that make, for example, I am talking and you know I am talking. How do you know I'm talking? How do you notice me that is talking? That information, that representation of myself in that audio is something that audio has in itself. It's something that the audio I'm saying has in itself. So you have things like speaker representation, emotions also is embedded into audio. So think of all of those. Think of all of those. So there's a certain way you would know that someone is being sarcastic when they talk. So all of these attributes is embedded into one single representation, and that is the audio, and that is audio. And so you see that it becomes a lot more complex. So, for example, now if I want to represent audio in a way that basically expounds on emotions, it's different from me saying that okay, I want to present audio in a way that expounds on speaker information. If I want to do something like classification, or for example, or tone, or I want to do something that would most likely only specify or expand a lot on the semantics of the audio itself. So by semantics in audio, I mean what the person is saying, right? So what the person is saying is what we call semantics in audio, and how the person is saying, how the person sounds like is what we call acoustics in audio. So combining semantics and acoustic gives us the entire audio information in the audio. Yeah. So where was that? Okay, yeah. So it's a lot more complex, a lot more problematic, but again, I would say that interesting problems are the more fun. So the more hard the problem can be, the more fun it is to tackle it. So it really proves. Yeah. Okay. So here, yeah. So let's step back and look at how audio is usually represented. So when we record audio on a computer, we don't use words or letters. We get numbers, right? So lots of numbers. So now if you remember the question I had earlier that if you were to write audio down, how would you write this down? So this is how basically computers understand audio. So again, this is not LLMs understand, this is how computers understand audio. So before we tokenize audio, it says to understand its raw form. So when sound is recorded, it's captured as a sequence of numbers, not words or letters. So when audio, so this process usually is so it involves taking rapid snapshots of the sound wave as it moves along a plane, as it moves many times a second, many times per second. So we call this thing this is what we call a sampling rate. So by sampling rate, we take the audio waveform, and then we sort of um take snapshots of it many times per second to sort of have it discretized in a format that we can give a computer. So yeah, I'm pretty sure I'm not explaining that very clearly, but think about it this way. We have just imagine you have an audio waveform in space. So let me go back to this thing right here. So think about this. So look at this diagram right here. Can you see this diagram here? Um, can you also see this diagram right here? Okay, good. So imagine I am taking, imagine thousands of times per second I'm taking a snapshot of a particular point on the plane, right? So let's say I'm taking a snapshot here, 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 like something like that. So and I sort of and then I sort of put okay that the minimum amplitude is let's say -1, and then the maximum amplitude is 1. Sorry, yeah. and then the maximum amplitude is 1. So if I kind of grid this thing right here, and then I put this in a grid, let's say I put this in is it where I can write down? I really want you to understand what I'm talking about. I don't know if it's possible for me to use my virus, my pen to write down. Okay, anyways, so think about, just imagine that this thing is in a grid, right? It's in a by grid I mean like what do we use to call this in a secondary school? That way we used to plot things in a graph, correct, thank you. So think about this waveform in a graph, right? And then the maximum possible amplitude is 1, and so like the maximum value you can get on the y-axis is 1, and then the minimum thing we can get to the x and then the minimum thing we can get to the y-axis is -1. And then and then when we are going on the x-axis, we are going according to time, like we are moving according to time, right? Do you get what I'm trying to? Do you understand that grid analogy? Anyone? A simple thumbs up is fine. Yes, good. Okay, thank you. I want to make sure I'm not talking to myself. Yeah. So when I take exactly, thank you, Hertz. Yes. So when I take as I let's say I now carry, if let's say I carry, let's say the Flash now, or Superman, people that run very very fast per second now, and then I run here. So let's say I run for, let's say 1 millisecond, right, on the x-axis. I take a snapshot of the maximum possible value, or of the point that of the point on the x-axis. I run again for another millisecond. I take another point. I run again for another millisecond, another point, and then and now so all the values of the y-axis, I arrange them down. So that is what we call audio representation in signal processing. So that's exactly how audio represents. That's exactly how computers represent audio. Not LLMs now, computers. So what they do is that they have a sort of grid, and then they take snapshots of the wave as it goes along the plane, many times per second, right? And then and then so the number of times that this snapshot happens per second is what we call the sample rate. Has anybody heard about sample rate before? Is it something anybody has heard about before? Good. So that's exactly what we call sample rates. So it's basically so now imagine this analogy. Now that means that if let's say we take if that imagine this, for example. Now, let's say we take snapshots 50 times a second, and then we take snapshot 1,000 times a second. Which would give the best audio? Which would give the best audio quality? Does anybody have, just think about the analogy, for example. So I'm trying to approximate this audio, right? And I take and then if and then I take a snapshot 50 times versus I take the snapshot 100 times per second, which would give the best clearest audio. Thank you, 100. Good, 100. Yes, because yes, 100 exactly, higher sampling, because I am basically approximating more times. So it's to give a final, thank you, not the word fine. So there's what we call cost versus fine. We'll see that word very, very soon. It will give a very much, it will give a lot more finite, a much more refined audio quality when we go higher in sampling rate. So I really love this audience. Thank you so much. That's a very, very, that's very intuitive of you. So exactly, thank you. I was about to go to that point now, but now there's a drawback, and I think this person already said. Now the drawback is that the higher the sampling rate, the more information you are, the more time you are sampling, the more data you are going to get, and that might be problematic. For example, if I want to sample hours of audio, right, and I'm taking sampling for our CD, our regular compact disc. If you are familiar with compact disc, so they basically do this thing 4,400 times per second, right? But for ASR, most time we use 16,000 to 4,000, because exactly 44, yes, 44.1 kilohertz. That's correct. I'm trying to, yes, Simon, you are very correct. So yeah, but in ASR we usually do from 16 to 24,000, because we are trying to know, because if you think about it, we don't really need that much fine grained information. But when we are going to something like text to speech or voice cloning, or things that when we are kind of generating audio, we would tend to use a larger sampling rate to get much more finer this, because when we approximate and we're a little bit coarse, and we're a little bit coarse in approximation with like 16K or like 24K, we of course we won't get fine information, but we would get just enough to understand what the person is saying, right? Do you get what I'm trying to say? we might not be able to understand. We might not hear what the person's. We might not be able to say that okay, this is the person that is talking, but we can say okay, this is what the person is saying. If that makes sense. So yeah, so in ASR we usually do 16 to 24, but of course in TTS or things that would need things like audio generation because we want our audio to be a lot more refined. We use a larger sample rate. So yeah, I really love this. Yeah. So you see, like exciting is I can talk about this thing for hours. So now this now let's go back to this. So this is how we would basically do that sampling stuff for in Python. So then we use the lab. So there are a lot of libraries you can, but I just use the library called Librosa. So areas like Librosa.load the audio. Sorry, I should add that this also takes a comma SR equals to something. So that SR. So this I don't think so. You can complete this if you want if you want the audio to be sampled in a particular sample, you can do comma you can do comma SR is equal to some. So Librosa.load audio comma SR is equal to some, and then you get and then you put the sample you want. You can be 16,000 24,000 441,000. So I think you can, if you guys can try it out later on. Of course, I'll make this available. Just do it and then see how the audio will sound like later on. But of course, we have a lab in a couple of minutes, so we'll of course see this thing in action very soon. So just bear with me. Yes, so as in the final example, the audio is essentially a long list of numerical values, each representing a tiny segment of the sound wave. So yeah, so why this raw numerical data is crucial for audio engineering, it's not yet in a format that language model can directly process. So the core question then becomes how do you transform this continuous stream of numbers into discrete tokens that a model can effectively utilize? Okay, so we have been able to arrange audio in a way that computers can understand. But now it's still verbose, it's still very it's still very it's still somewhat unsuitable for language model because if you think about the way language model taking text taking information just imagine it so they take in information with based on of numbers I think I explained that here so they do one two three so they take in discrete tokens but this will give you some sort of continuous information so it will give you let's say floating point numbers 0.1 0.11 0.25 something something but other data they take in things like one, two, three, four, five. Do you get what I'm trying to say? If you get what I'm trying to say, please just give me a thumbs up. Good, yes. So that approaches to audio tokenization. We can broadly categorize audio tokenization into so we can broadly categorize audio tokenization into two segments. So actually in real world you wouldn't see this analogy used, but I kind of simplified it this way so we understand it. So this decision exactly you won't exactly see this decision in the real world, but it's something that I think it will be helpful for you to understand how exactly this works. So here, so the first one is continuous representation approach. So here, raw audio is transformed into continuous features like spectrograms, spectrograms, and embeddings. So these representations preserve high fidelity. So they capture details like timbre and speaker identity. So many speech recognition systems like Whisper. I don't know if anybody familiar with Whisper. It's a popular ESR model, open source. So yeah, so these benefits contains rich audio information, but the challenge is that language models don't naturally think in continuous signals. So I said before that models take in discrete informations, right? But this continuous representation, it's not exactly the way that models can easily that language models that are familiar like Llama, your Quen, your Gemma, they can exactly ingest. So um yeah, so people, of course, but this is the best way to represent audio, to be honest, because you are not sort of compressing, you're not quantizing, you're not doing that. You are kind of representing audio in all its beauty. So by beauty, I mean that in direct representation, every single part of audio is there. You have the speaker information, you have the timbre, you have the amplitude, you have emotion, all sorts of that. It's represented in the dense, rich, constrained representation. So I don't know if anybody has played around with RAG-based systems before. Retrieval augmented generation. Anyone? Yes, good. So now in RAG systems, that means you must be familiar with text embeddings, right? So what comes out of text-based models? Text embedding models. So that number, like those rich, compressed numbers, that's exactly how continuous representation looks like in audio as well. So it looks exactly the same in audio as well. So in that representation, a lot of very rich information is there. It's imbibed in. So we as humans might not be able to say that okay, this number means it is audio that is talking, or this number means that it's someone else that is talking, but the computer can understand it. Yeah. That's continuous representation. But now another one is now the next one that I think might be interesting for is what we call discrete representation, the approach. So this method takes all a lot more further. So it compresses and it concises. So that representation that we get from continuous representation, right? So it's concise is so discrete representation approach concises it and so it's decompresses it a little bit, compresses and then it's concise. So it's and it concise. So by quantization, we convert quantization is basically a technique of converting continuous based information into discrete based information. So it's basically I'm converting dense information to one not encoding one not information where we are having integer instead of numbers. So you see convention everywhere. You see convention where we are trying to make models faster in production. You see convention in ways of where we are trying to kind of do interesting things. Even outside of AI signal processing, you see convention in lots. You see convention in things like it's a very very interesting thing. I think it's very very particular. It's a very very exciting area of ball. So we took that area of research in signal potential and we apply it in audio here, where we basically take in the cost representation and then we compress a little and we concatenate it into a finite set of symbols, an alphabet for sound, for example. So this makes audio resemble text, allows models to leverage familiar text-based tools like cyclic modeling and next topic prediction to do interesting things with audio. So, of course, we'll see an example in a bit, and when we go into our lab, but yeah. Um, sorry. So this is just a simple table to understand the differences. So in continuous representation, we audio is kept as continuous features, while in discrete representation, it's compressed into a finite set of symbols, tokens. So analogy is like a photo with symbol, while this one like pixel art, so with limited color palette. So of course, now fidelity, of course, continuous representation will keep things a lot more high. So it gives your details, so it gives them very high details, and it's very good for reconstruction because it's by construction I mean that we are taking those continuous information and we are taking it back to audio. So a very very interesting research idea for anybody that is very very inquisitive is can you try to figure out a way to convert text embeddings back to the text themselves? Just think of a neural network you can train that can do that. That's a very very interesting research, a very very interesting project you can work on. So if you are familiar with audio embeddings, text embeddings, so try to figure out a way you can train a neural network and go from those text embeddings back into the text themselves. So that's what we call reconstruction. It's a very that would probably be a boost on your portfolio, but just try and see if you can make it work. So that can be an assignment for you. But let's go back to audio. So, but that's all reconstruction and in continuous representation. This is very very easy for you to construct continuous representation back into the audio themselves because you don't do a lot of compression, right? The only compression type thing you do is that something that we are doing that we're taking snapshot because of course some information will be lost, but not as much as discrete. So this representation is a lot more lossy because you're compressing and quantizing, you introduce a lot more loss. So your reconstructions are a lot less crisp. Um, yeah. So consumer essential is most like ASL pipelines, switch features like Whisper, while the scripts audio tokens are used a lot in spoken words, but of course you still use them. We use them a lot in ASL too. And TTS. But so we won't do this in our lab. We'd use this information to train ASL model. But yeah, so now let's zoom in into discrete tokens. So the core idea between behind discrete tokens is to convert. I think I've talked about that a lot. So I won't just bore into how exactly discrete tokenizers are trained or are built, but I'll just give you this I'll just like you to check some of these projects for you to understand exactly how this. So I'll give you this slide later on. But I really want us to go to our lab so we can understand all of these things I'm saying because I'm yapping, I think. But when we go into our lab, we'll see how these things work. Yeah, so Encodec is a very popular. It's the more popular. It's the first it's the first discrete tokenizer that was used to add audio features to language model like 2023. Of course, nowadays it's not seen as much use because it's not as good compared to ones that have come out recently, but it's still what I'm talking about. So so the research is very foundational. I won't again bore in how it was trained exactly, but yeah, you might want to just read up on it. I want us to what why am I talking about this? Why do I see it as important to dedicate a whole session to talk about it? So what can you build with audio tokenization? So you can build something with ASR, so converting spoken audio into text by analyzing the sequence of audio tokens, voice assistant, transcription services, text to speech, for example, where you take already pre-trained language model, you take already pre-trained open source language model like Quen or Llama or whatever. If you have compute, you can go the DeepSeek approach. If you have like a bunch of H100, go the DeepSeek approach, and then you had audio correlating to it. So by adding audio correlating to the model, you are giving it, let's say, here to listen or a voice to say, to talk, to use. So basically, you can have that language model be able to respond in audio, or listen in audio and respond in text. So basically, that's so you can do things like voice cloning, conversational systems, audio compression, and creative audio generation. Yeah. So good. I think we're done with talking. We are going to code now. Any questions? Okay, I think questions are after it. But are we all flowing? Please, if you are flowing, please give me a thumbs up. So I'm not talking to myself all this while. Good. Yes, thank you. So now let's go to our lab. So we are going to go to a collab document now. Um, so we won't spend a lot more time. I'll be doing into something that I show you. So we leave here in time. Good. Um, oh shit. Oh shit. Shit. Let me just share my screen back. Good. So this is a collab. I know we are familiar with collabs. So I won't ask that very silly questions if we are not familiar. Definitely, it's for you. I'm going to make it available to the team at ML Lagos for you to play around with. So this is a very simple, very simple project. If you feel free to work, feel free to improve on the project. Feel free to work on it some more. But yeah, it's a very simple proof of concept on how to do some of these things I do. So I'm going to talk about why I did some things here. So bear in mind that this code is extremely so you won't see this in any production. Basically, it's a very I wrote this in 30 minutes. It's a very it's not very the code is very inefficient. I would say you see a lot of squeezing of tensors. So we're going to use boy, don't crucify me. I apologize in advance. But yeah, the code is not very it's not very efficient for it to work, and I think it's going to help us a lot with how exactly this works. So yeah, let's just so this is collab. Let's just pip install transformers. Transformers is a very popular ML it's a very popular library by the folks at Hugging Face, a very wonderful team at Hugging Face. So they basically make open source tools available to GPT poor people, GPU poor people like me and you. Sorry to say, yeah, Hugging Face exactly. So data set also is a library by Hugging Face. So we have Librusa and Soundfire. I think you remember Librusa. So this basically are two libraries that we use a lot with audio manipulation, audio manipulation basically. So we have Touch Audio, of course. So this is Meta's de facto audio manipulation library. So all of these things are just we have Snack. So Snack is our audio tokenizer for today. Let me just audio tokenizer for today. Again, I won't go deep into how these are trained or how they build them. I really want us to understand just how to use them. But again, feel free to please go through it. That's the benefit of being ML researchers. We are very inquisitive. So feel free to understand how exactly they are trained, how they work, the intricacies of things like RVQ, residual vector quantization, or things like FSQ, finite scalar. Okay, I think I'm talking too much. But yeah, this is people installing this. Now let's run this. So we're running this basically. So I imported PyTorch. I think are we familiar with PyTorch? Don't worry, it's not going to be very. I assure you, I would not. I will try and explain a lot what I'm doing. So we installed the audio tokenizer here. The OS library is basically how you manipulate OS operating system based. Oh, I'm sorry. Okay, don't worry. I assure you, I would explain a lot. I will try and explain a lot. I know I talk a lot, so I will use that a lot now. Um, yeah, and then we have data sets import, load data set and audio. So this is basically just the Hugging Face library. So again, don't be intimidated by all of this. So this is just basically something we use to download our data sets, right? And this is basically and this is basically what we are going to use to kind of set the sampling for the audio in data sets. So yeah, there's now here we are basically just setting because we are using. Are we using a GPU? Let me see. Oh yeah, we are using GPU code. So basically, we are basically here saying that we want to use a GPU instead of a CPU here. So we're basically telling PyTorch that please, oh, bro, I have a CPU, I have a GPU in this machine, but please use my GPU to make this look more faster. That's basically what this line does. So yeah, we are going straight into our. Now let's now download our data set. So I'm going to just show you what it looks like in Hugging Face. In a minute, I'll share my screen right now. So give me 1 minute while I kind of show you what this data set looks like in Hugging Face. Again, don't be intimidated by what this looks like. This is just basically a Hugging Face data set, right? Um, so this is the audio and this is the text. So what we are training, we are training an ASR model, a speech to text model that goes from audio to text, right? So our model should at the end of it, of course, we would. I think we will not have chance to wait for the model to finish training this segment, but again, you can feel free to. But I assure you to do what should work. So you can feel free to try and wait till the end or for the model to train, for the model in our lab to train, and then you can see if it's gives. So this is the audio. Okay, let's play it and see how it sounds like. Um,
Black people talking in the marketplace.
Okay, so let's do this
Two
one.
workers attempt to stop a flooding street.
Can you hear the audio? Do you hear the audio? Good, good, good. And then this is the text. So we're basically training a model that can take in this audio and give us this text. Yeah, that's what we are training. So this is the data set. Now let's go back to our lab. Um, yeah. So here we're just basically downloading the data set here. Um, non-proc again, don't bother about all of this very annoying argument, please. I didn't want to waste my time, so I just set this one to for the model to download much more faster by using all the processors in this machine. Again, don't bother about it. You don't need it at all. We are going to a very interesting thing. You don't need to worry about all of this very noise making thing. Don't worry about this. Sorry, I should have done that earlier. So now let's download our data set. So we'll just give it a minute, a second or two to download. Good. Yeah. So got our data set. Now let's inspect our data set and see how it is. So now let's do this. Import the browser. The browser is what I showed you earlier. And then we are going to now do from. So this basically is just a way for us to visualize the audio in our notebook, play the audio in our notebook. So the same audio we played on that on login fee, we are going to play it here. Good. So now we are now going to cast some. By now, this line basically is very interesting. Now we don't know exactly what the original data set sampling rate is. But what is done is just the organ face, a organ face way of saying that okay, oh, bro, please, whatever the audio is in, please just help me to set the sample rate to 24,000. You remember I said that in ASR we can use any sample rates up from let's say from 8,000 to like 4,400, but we tend to use 16,000 to 24,000 sort of save our GPU VRAM because to be honest, 44,000 is much of an overkill because a lot of information we need for the semantic information we need for ASR is already very much represented in the sample rate like 16 to 24,000. Yeah. So we just cast our audio here, right? Now this line is just to set this is just a Python way of just setting the data as an iterator and then selecting the first role in this data set. So basically, we are selecting the first role in that data set now. Now let's now play this. Oh, sorry about that. Just give it a minute to load. Um, yeah. So this is our audio, right? And this is our. You know, I said that you know, I asked how do we write audio. So you see this. You see why audio tokenization is very hard. It's not hard. It's not easy to write audio, but sampling is just the way we use it, just the way we do. But of course, I mean, there might be a very smart people and very brilliant people on the call right now that can take all of this problem I'm talking about and just develop problems. So feel free to reach out to me about the weirdest ideas you have. I love talking about things like that a lot. So yeah. Then the sentence and the audios. Okay, now let's go back to our audio. Now let's now play the audio to this thing. Let's play it. Yeah. So we just again don't bother about all of these things. Like I said, this is very inefficient. You won't see this in a production environment, but please bear with me. I just want you to understand how it at least works. So yeah, so the audio array is basically row.audio. So I'm selecting this audio here, and I'm saying get all samples. Don't worry about all of these things again. You just want to get the audio. Now, you might said that we take a snapshot of the audio on a grid. So this is the value of that snapshot on that grid. Do you guys what I'm trying to say? Can you guys see this? Yeah, so this is the value. So now this is the result of sampling, right, on that grid. So of course you are seeing things like so you are seeing things like 9 7. So we basically take those snapshots many times a second. Now our sampling rate is 24,000. So we take that snapshot 24,000 times per second, right? And then this is our result. This is our result in the array. Yeah, yeah. So this is our result in the array, and then yeah, so this is it. This is a result of that whole process. So they will just load this. Now let's try and play this audio. No, it doesn't have 24. No, floating point. No. So okay, but no. So 1 second of audio corresponds to 24,000 points. To 24,000 points. But no. I would say don't worry, I'll get back to that in a bit. I don't want to. I want us quickly. I think we have 10 minutes or so. So yeah. So now let's play that audio. Let's play that audio here.
I'd like to know where he is heading at.
Yeah, so do you guys hear the audio? So this is the audio. Now let's now see how we're tokenizing with Snack. So now we do our audio tokenizer, we send it to our GPU. So this two device sends our GPU, it's a PyTorch thing. Please don't be infected by this, it's a regular thing. Yes, so now we would now put this same audio array again, because I said that it's very inefficient, because why am I first of all sending this tensor to a numpy array, and I'm coming back again to now put this back again into a tensor? It's not efficient, it's wasting GPU, but I did it, so please pardon me. Yeah, so we made that into a tensor, and then now we encode by encoding. Now this is our audio token. When we encode, this is our audio token, and by constructing, tokenizers. What tokenizers basically do is that you can send the audio into tokens, and then you can convert those tokens back to the audio. So that's basically what is happening. So now from those same audio here, I'm now tokenizing them back for you to see that okay, we can actually convert from audio to token and from token back to audio with this version. Now let's play it. Now, sorry. Okay. Please don't be too don't worry. I show you it's very easy. So basically, I take this audio array, right? I convert it into a audio token, right? It is a very lossy process, Matthias. Very, very lossy. This particular one is, yeah, that I love that question. Very, very lossy. And I'll talk about that in a bit. So by lossy, it means that we are going to lose some information because we are compressing and we are quantizing. It's natural, it's a problem. And that's why I don't like this version of token. I think if you follow my tweets on Twitter, I talk about it a lot. I don't like tokenizing things with this method, but this is what we use in industry today. Labs everywhere from OpenAI to Google. This is what we use nowadays for not this fast tokenizer, but this version of it. And it's a problem, it's an area of research. And again, we can come up with something that people will use. It's a area of research. We can always come up with very interesting ways of doing this thing. But yeah, it's a very very lossy thing, very very lossy thing. Yeah, discrete tokenization is very very lossy. So now let's now since let's now see how the audio tokens look like. Now let's now play it. Let's now look at it. So do you guys see this now? So you know that this now resembles a lot. So this is our audio basically. This is the result of quantization, right? Now imagine this is all our audio information. This is what I'm going to talk about what we mean by lossy. So this is all our now the tokenizer is saying that now the tokenizer is saying that this now the tokenizer now is not telling that this is all of our audio information. Now you can see, of course, you asked me that, but bro, how is it that we are representing audio that is very, very rich in information in just these tokens? So this is what we mean by lossy. By lossy, we mean that the process of tokenization, the process of tokenization would lose a lot of information, right? But of course, we can still reconstruct things to what. So now, some of this information that we lost might be inconceivable to our human ears. So we might not be able to see the information that is lost. So we might still be able to hear the audio sounding very much the same thing. But trust me, a lot of information is lost. And when you go to some very very nuanced things like TCS, you would see the effect of this lost information. But for now, it is fine, and that's why in ASR I basically okay. That's an ASR. We don't exactly use this mail to mention ASR, but we will just use it for this process. So now basically this is trying to say that this all of these tokens is what our audio represents. So in these tokens, we would see every single thing that this person said, and that does not make sense. But it doesn't make sense, but it works. And yeah. So now in Snack, there are different ways. Again, each of the tokens do things differently. But in Snack, this is what we call our cost token. This is what we call our fine token, and this is what we call our final tokens. So basically, it's like I kind of do uh this is what we call VQ, vector quantization, basically. So it's a loop, it's a loop process where from this guy we get this guy, from this guy we get a lot more final information from this guy. So again, don't bother a lot about this, but we'll talk about this. Don't worry a lot about it, but feel free to read if you want to understand it better. Feel free to read up on Snap. Let me just put the link to the repo here. There's a lot of audio tokens out there. So we call them discrete audio tokens on sometimes, but let me just add the link to the repo here. So you can feel free to just check out this. Yeah, it's learnable. So we learn it based on with the code book. You know, I really don't want to go into the theoretical part of it right now. But yeah. Now this is what the constructed audio looks like, basically. So again, this is the actual audio, right? And then this is the constructed audio. So this is the result of converting this definition back into audio. Please, are we all flowing with me? Please, any thumbs up is fine. Yes, good. No worry, we'll soon be done. Soon we should be done. Let's now play the actual original audio. This is the constructed audio, and this is the original audio. So remember I said before that sometimes you might not hear the difference in you might not hear the effects of the lossy process that tokenization does, but yeah, if you can hear now, I think if so this is so if so you so this particular thing is not as high quality as this guy right here, but sometimes we as humans cannot hear the loss in information in. So let me just play each of them. So this is the original,
I'd like to know where he is heading at.
and this is the reconstructed.
I'd like to know where he is heading at.
So you see, it's very, very hard for us to get the difference. But trust me, a lot of information is lost. Do you guys hear the audio? Okay, good. Now let's now set our language model backbone. So we use a small LM. So that again, again, what we are trying to give a language model, a preacher language model, a hear to hear. So basically, it should be able to hear audio, and then with the audio transcribe whatever text we give. So now because we have given, so now you see that we have given since we have numerical information, now we can just pass this numerical information to language model. But the problem is that the language model already has its own text-based vocabulary, so we can't exactly say that okay, we want to give it this thing verbatim. We have to do some interesting things to it. So naturally, you'd want to do things like extend the vocabulary of the language itself to kind of accommodate all of these new tokens. But for us right now, I won't do that. I won't push. Right, what I'm just going to do is just very, very dirty thing. What I'm just going to do is I would just turn that thing into a list, into a string. I will just turn this. I just turn this audio tokens. So those audio tokens into a string, and then I just pass into a prompt for the model. So it would work, but again, this is not exactly. This is not going to give you state of the art or something like that. So do expect to be able to compete with OpenAI or Gemini or speech with this. Don't attempt to compete with speech with my company with this process, but it works. Yeah. So yeah. Um, let's now run this. I'm going to run this guy right now. So now basically what I'm doing is I'm passing in the audio tokens into this simple prompts, right? And then I'm now going to tokenize it with this tokenizer. And I'm now going to delete this. I'm deleting these things to save GPU memory because we're on a collab. I can't exactly go all out. So yeah. And then we just tokenize, we use this function tokenize, and then we now map this thing. So this is technically going to take time. So I'm not going to wait for 3 minutes for the video to be done. I have already done this before, right? I've run this entire this before. So I'm just going to load the data set I've already tokenized before. So we don't have to wait for 3 minutes for this to be over. I'm just going to download this thing again. So this data set basically is me before I'm playing with this column. So I've done this when I push this to Hugging Face. So now I'm just going to download the preprocessed data sets already. you can feel free to let this go all out and comment this out for you to just be for you to just run everything through. Yeah. So we're downloading the preprocessed data already. And now we are going to have a equalate function. Now, again, we are going deep into how touch and Python handles data. But please, again, don't worry. I really do. I don't need you to, I don't want you to understand it. I'm not exactly in it for you to understand how exactly this thing is. How I'm not exactly one. I don't exactly want you to. I'm not exactly here to teach you guys how to do PyTorch or PyTorch exactly. I just want you to understand the context. The context. Yes. So I'm going to now play this guy right here. Okay, I've run this already. So this is the collect function basically, and it's what a data loader takes in. A data loader is basically is basically an iterator, right? For a Python, is it iterator in a Python loop? Yeah. So now let's just run this. So this is our training loop. Now what this does is that first of all we load our train it and our test data from what I already downloaded before, right? And then I kind of build a data loader from each other. Again, please, I'm sorry, but honestly, I just need you to understand how audio was tokenized. I don't really need you to kind of don't be bothered a lot unless when you're doing it on your own. Don't be bothered a lot with all of these things done. So this is just a very simple way of building an iterate over our train data so that we can use a for loop of our train data to kind of ingest. So what data loader basically does is build a for loop, right? An iterator basically. So with a for loop, we can ingest data into our models in step by step, right? So now we calculate our loss. So again, language models are trained what we call next token prediction. So what we do is that again, don't bother yourself a lot about cross entropy. So it's just we are shifting the model and then we are just doing some interesting we are shifting the model one step at a time so that the model takes in. So what the model basically the model takes in all of the sequences with all of the sequences and then that's all of the sequence and then the label basically is the sequence the sequence shifted one step into the future. So let's say the model takes in my name is the label would be the label would be name is Odu. Do you get what I'm trying to say? So just I'm trying to say please. Okay, I think a lot of people have lost me, but please don't bother about the calculate function. I also want you to just see this thing in action. Yeah, so this is optimizer. Again, don't bother a lot about the regular Python training loop. We are sending our model to our device, our GPU, so that it would not blow collab here. And then we'll set the number of epochs, and then we can train. We train, yeah. Lots of backward, we compute back propagation, we step it, and then we zero out our gradients because we want to under step. Yeah, now we are training. This is our train loss. It's going slowly, small. I'm not going to let this train fully, but I'm just going to give you this collab notebook for it to just play around with. Yeah, and I think I'm basically done. Yeah, and so when this is done training, you can feel free to use this. I put this function here for you to just play around to see if you are able to get transmission from the model. Again, it's not going to be accurate. It's not going to be that good, right? You would just what you see is give you something interesting. So yeah, I think I'm done for now. I don't have anybody. Okay, I think I'll let Ifeanyi. So thank you for coming to my TED talk again. Hopefully I did not bore you with with things like this. But yeah, feel free to reach out to me. I love talking about things like this a lot. So yeah, I'm just going to stop sharing my screen. Thank you guys.
Thank you everyone for joining the session. As usual, the session will be recorded and it will be posted on our YouTube channel. Right. Some upcoming events you have the October technical session and the October office hours. And if you have any feedback at all, you can send a message to the link I've sent to the chat and tell us your feedback. Thank you everyone for joining the session. Yes, the meeting is being recorded and it's going to be uploaded to the Machine Learning Lagos YouTube channel. So yes, thank you very much for joining.
Thank you for having us. Thank you for a great session. Nice one. Have a blessed weekend. Bye bye.